Hello and welcome back. In this third example of optimization, we're going to be looking at trying to find the points on the curve given by y equals the square root of x plus 1 that are closest to the point 2 comma 0. And to do this, we're going to once again draw a diagram of what is happening with our graph. And we have the square root of x plus 1, which crosses the x or touches the axis at -1 and goes forever to the right, increasing. And we have the point 2, 0, which is fixed. And again, we're measuring the distance between points on the graph and that fixed point on the axis. So our distance goes from here to there. And our point is going to be x comma y, which is going to be able to move along the graph. And again, 2, 0 is fixed. So the first thing we want to do is we want to go through and recall the distance formula from pre-calculus or college algebra. It is the square root of x2 minus x1 squared plus y2 minus 1 squared. And in this formula, you will notice that again, we want to make this as simple as possible for ourselves. So we're going to make the x1, y1, we're going to make that our point that doesn't move. And then our moving point is going to be the x2, y2. All right, so our x2, y2, we're going to call that just plain x for now. So it's going to be x minus 2 squared, and then y minus 0 squared. So that's our distance function. And again, it's in terms of two variables. It's the square root of x minus 2 squared plus y squared. And just as we've seen in other examples, we have our constraint that we have to use to reduce our optimization equation or our objective equation down to a single variable. And we know that the y is always given by the square root of x plus 1. That's the graph we have. So we're going to replace that y with the square root of x plus 1. So our distance function in terms of x is the square root of x minus 2 squared plus the square root of x plus 1 squared. And we can then simplify this down as the square root of x squared. Make that a little nicer than that. So square root, again, x squared minus 4 times x plus 4 plus x plus 1 from squaring the square root. So we end up with the square root of x squared minus 3x plus 5 inside of our square root. And now we're going to apply the rules of calculus to find our minimum distance. Minimum is closest because we are minimizing the distance between the points. So to do this, we will find our derivative. And our derivative, remember that this is an expression raised to the half power. So the derivative will have a coefficient dropping down. And then the power is going to reduce by 1 to -1/2. And then we have to multiply by the derivative of the inside, which is 2x minus 3, using a chain rule. So our derivative simplifies down to a numerator of 2x minus 3 over top of 2 times the square root of x squared minus 3x plus 5. And if you want to think of it this way, this is 2x minus 3 over 2 times d. Because remember, the square root is our distance. So remember, the distance is never going to be equal to 0 because the point 2 comma 0 will never be on the graph of the square root of x plus 1. So we know that d is never equal to 0. So because d is never equal to 0, we know that this derivative is never undefined. But d prime could be equal to 0. and d prime of x is equal to 0 when 2x minus 3, the numerator of our fraction, equals 0, which means that x is equal to 3 halves. So once again, we draw a number line, and we put our derivative on the number line, and we know that at 3 halves, our derivative is equal to 0. And of course, we can't have anything smaller than, or again, we don't even have 0 here as an option either. Well, we actually do have 0 as an option, but it's not going to be part of our answer. All right, so next thing to do is now look at, again, comparing the sign of our derivative for the two different sides of the number line. So again, our derivative is 2x minus 3 over 2 times the square root. We can pick the number 1, which is less than 3 halves. So if I take a 1 and I substitute it into my derivative, you'll notice that I get a negative number because the numerator is negative, my denominator is always positive. So when x is 1, my derivative is negative, and that's going to be true for that whole interval. Something bigger than 3 halves, such as 2, substituting in my derivative, I get a positive value for my derivative. So I know that my distance is decreasing up until 3 halves, and then from 3 halves on, it is increasing. So the ordered pair with x as 3 halves is going to be the closest point on that semi-parabola or half parabola, if you will. And then we need to actually find the value. So we know that if x is equal to 3 halves, we know that y is equal to the square root of x plus 1. So y is going to be the square root of 3 halves plus 1. So y is going to be equal to the square root of 5 halves. So the square root of 5 halves is the point, the y-coordinate for that ordered pair. And that right there is the point that is on the graph, when it's all said and done, that is closest to 2, 0. So again, this is our going to end up being 3 halves, square root of 5 halves for that location right there. All right, so that right there is the optimization problem for our point closest on the graph. I will add the one little comment that you actually could also minimize the square of the distance and avoid all the square roots and the derivatives, but we just wanted to kind of go through and take the derivative with that square root because it's really not too bad if you use the chain rule.